It has all the necessary stuffs for the last part of your syllabus, the way I progress the syllabus. And in essence, these three chapters, which you're going to see over here, direct sensing, emergency, and communication information, which are three different worksheets as well, they this booklet was actually compiled from the earlier version of the uh, CRISME, Mike Crandall, International AS and O level, AS and A level physics book from that one. So most of the information that you are gonna see over here, most of the figures that you're gonna see over here are gonna be quite similar to that book. I mean, this one, Mike Crandall. This is the second edition. So it has this cover. It's a bit abridged, shortened. So the first edition was actually even better, in my opinion, and it had more information. Now, one thing I'd like to take your attention about this thing is that this idea of having the whole thing divided into two sections is no longer valid for your syllabus design. Currently, they have embedded this whole section beyond the application of the physics in relevant chapters. So I'm going to first show you that part, and then I'm going to jump into the discussion of the content of the of these chapters immediately. For example, the first thing that we have is the in the application booklet is the direct sensing. So what direct sensing is, this is about the application for the operational amplifier, which in your syllabus is introduced in, I believe, oops, here in the chapter of electronics. So electronics chapter is located between capacitance and magnetic field. So it's possible that they're gonna give you problems from the direct sensing worksheet in around this chapter. So you have all the stuffs over here and everything, and then comes the op amp. This is the circuit symbol for the op amp. It's a triangular shaped device. For the circuit symbol, practically it's a rectangular, can be of any other shape. And how does the whole thing works? And what does this thing mean? These things are actually given over here. So that's one thing. So the direct sensing is already discussed over here. Then we have the remote sensing. Remote sensing is basically detecting information from a further away distance without actually being present there. Or so it has a lot of medical imaging preparations, for example, ultrasounds, MRI, CT scan, basic X-ray. So these are the four different topics which are covered in the remote sensing heading, which I believe would be available in this chapter, medical imaging. So here we have all of this remote sensing parts. So first we have the X-ray, then the X-ray behavior, characteristics of the X-ray, how this is happening and everything, X-ray attenuation, and a lot of other information as well. So we have how to improve the X-ray images and lots of new figures as well we have. So this is how the, so we can actually take a lot of reference from this part as well. But I'm mostly comfortable teaching from this booklet because this actually has a lot of information, but we can also go by this chapter as we slowly move forward, either from your textbook, or we can go from the Mike Crandall textbook as well. It doesn't have a index on the left side, so might as well look up for the index at the very beginning. This one also has all of those chapters in certain order, which I believe is possible to find out. Let me have a look. Here we have electronic sensors. This is the op-amp. These two chapters, these are the op-amp stuffs. And then we have communication. Communication is basically this third chapter that we have in this booklet, which is the communication information. How does this work? There was a bit of a change in this chapter. That is prior to, I think, 2011. the mechanism for the cellular network channels, that how does a cellular network operate within a given range of space, was included in your syllabus. Not the very detailed level, but at least the flowchart diagram, that what is the pathway for the information. So what is the flowchart for information mechanism that travels from the cell phone through its different processes, and eventually it goes to the antenna and comes back and eventually gets reprocessed to give you the sound. So voice going through antenna through the communication channel, becoming sound on the other phone, and vice versa through the channel. So this was included, which they have discarded, I think, from 2009. So I actually, so 2008, 2011. So I deleted those pages from this booklet, which is no longer included here. But if you download this booklet directly from the CAE website, you'll have a bit more pages. This one is 40 pages. So that booklet was, I think, about 44 or 46 pages, something like that. So this one has everything that we need. Or so there's a communication chapter. The point that I'm trying to show you over here, that why these individual stuffs of the 3 chapters that I'm going to show you are gonna be available in your book. So here the communication system is chapter 20. This is the communication systems. So they have all of the stuffs and everything. They have placed this right after the oscillation, because oscillation and energy intensity, these are pretty importantly related to the idea of communication for signal strength and stuffs. And then we have electronics, which is the op-amp. And finally, we have the remote sensing, which is the medical imaging. So these are the 3 contents that we're going to look for. Stuffs that will be discussed over here. Let me be very bold to you that I cannot answer a lot of whys for these chapters, because I did not study about them, and I don't need to explain those why parts for your syllabus requirement. There are a lot of whats, that what happens when something is done and how that happens. Most of the whys are not discussed. So I'll not be able to answer a lot of whys, that why does it happen this way, or why did it not happen the other way around. I wouldn't be able to answer those. And the key requirement for these chapters are for you to understand the purpose of these devices for mostly our regular life applications. For example, operation amplifier is actually a combination of a lot of transistors within itself, whereas a transistor is actually a 3-part it's a 3-part diode sandwich, where you have PNP or NPN sandwich together, which gives you the amplification capability. Operation amplifier is actually a complexly arranged transistors which behave in a very specific way, and the name itself says that it is operational amplifier. So you do understand that its primary purpose is to amplify a signal, which means you feed it a weak signal. Weak signal in this case means you feed it a weak voltage, and then that weak voltage can be converted into a much higher voltage. If you wonder that what is the difference between a signal and a voltage, that can be understood that we can have a lot of different communication channel. So that's the first thing that I would like to discuss. Here we have in this, not in this chapter, I mean here you have in the 3rd chapter, if I just show you, because op-amp, the purpose of the op-amp comes a bit later. So these are 3 possible communication channel that we have. You can see that we can really talk to a person, which is possible to achieve in a very small distance. The second thing we can have is that we can have a wire-based, only wire-based electromagnetic mechanism. So we can talk into a microphone, which is going to do some vibration, and that vibration in the presence of a magnetic coil will produce some specific characteristics, electrical voltage variation. And if we send this voltage variation information through a pair of wires, which is called a wire pair, to the receiving end, that same voltage can cause another loudspeaker to vibrate in the exact similar pattern. This thing is also another communication channel. This is possible to achieve within longer distance than A, but this is not possible to achieve for a really long distance because of the resistance of the wire. As the voltage would have to travel further, naturally its value would be slowly becoming smaller, smaller, and smaller. And eventually, if the wire is really long, we are not going to be able to actually understand what the person said on the delivery side. So it has its benefits, it has its disadvantages. So we're going to see about them later, but it's just another way of communication, another channel of communication. That's the word that we use, channel of communication. And in number 3, we have the third way of communication, which is the most popular way of communication currently we use these days. Even for short distances, we can also use them because we are trying to call up per person from within the same apartment from one room to another room. We don't even bother shouting their name. We just put missed calls in their phones and people show up in your room. So I would say C is the most common way to call up people or communicating people. You can see here we are talking through a microphone. Right after the microphone, we have an amplifier. So that amplifier is going to amplify your voice and convert it into voltage. A microphone converts the sound wave into voltage. We're going to see how the microphone does that. We have this in our discussion for this within these chapters. And then that voltage variation is fed through an amplifier. The amplifier receives that signal and makes it large. So it keeps the shape of the wave, or it keeps the digital values of the signal exactly same. It just adds bigger magnitude in places. So it just magnifies the whole thing in the exact same property. And then it sends that signal through an aerial, that trident thing that you can see at the end of the amplifier symbol. This trident looking thing is the antenna or aerial signal for aerial symbol for electrical circuit. In this aerial, that voltage is going to produce an oscillating electric and magnetic field, producing electromagnetic waves. So this is gonna send out this voltage variation in the form of electromagnetic wave in the space. This antenna, if it is properly tuned, we're gonna tell you a bit later that what does it mean by the word tuned. If it is tuned to receive this signal, then it will this antenna will resonate with the electromagnetic waves that is of this part. Because you have to understand that any antenna you can think of, if you think about it, it is actually surrounded by a lot of electromagnetic sounds or electromagnetic signals around itself. If you want to pinpoint one specific signal and be able to pick that up, you have to make your device to be able to resonate for that exact frequency. And we can do that. And in that case, this electromagnetic wave would be picked up by this loudspeaker. And because within this space, the signal has to travel up quite a lot of distance, it would also become weak. And not only it will become weak, it will also it is also possible that it will pick up some unwanted noises from the surrounding. What unwanted noises are, I mean, what do we mean by signal noise? We're gonna discuss about that in more detail later on. But however, this is picked up over or in this antenna. And because this signal is pretty weak, we are gonna send this to an amplifier once again to make it stronger so that we can actually hear it. Then if we run it through a loudspeaker, we hear this same sound. So this is basically how a cellular network or a wireless network works. So this is applicable for walkie-talkies, it's applicable for cell phone communication. Walkie-talkie is a direct working mechanism where you have device to device. You don't need any antennas for walkie-talkies to work. Whereas if you want to have a cell phone network or cellular network, then within this communication channel, you need to have a series of physical structural backups, where from one cell phone, it actually, this information doesn't necessarily only go through the electromagnetic wave form. It is also picked up by an antenna, it is magnified, and it eventually is sent through other communication channel as well. One of the communication channel, very popular communication channel, which is not shown in this figure, is the fiber optic communication channel or the optical fiber. So that is not given in this figure. They could have put this as an information number D. We can also send information at a pretty high speed with very high efficiency and very high bandwidth. The word bandwidth will be very commonly, very rapidly used for this chapter as well. The word bandwidth essentially means how much data can you send through a communication channel simultaneously. How much data can you send through a communication channel simultaneously? So one of the ways that is easier for you to understand, uh, bandwidth can be compared to something of like the width of a highway. If your highway has small width, then you cannot pass too many traffic through it. The number of traffic that can pass back and forth would be small. If the width of a highway is pretty large, you can pass a lot of traffic per second or per hour. So bandwidth of a communication channel is something like that, that how many bits of data can you actually transfer per second. This is, there are a lot of limiting factors which can give us a final value for the uh, bandwidth of a communication channel. So I mean, there are physical factors based upon what type of communication channel are you using. For example, if you use this one wire pair, and if you use an optical fiber, typical optical fiber, these are two choices of medium, which is going to give us two different bandwidths because of their own physical property. And then again, what kind of mechanism are you using on this side to convert this sound into an electrical signal, and what type of mechanism are you using over here to reconvert that electrical signal back into sound. That these two, the capability of these two devices also matter. So there are a lot of limiting factors which can give us a limit for bandwidth, but bandwidth essentially means the uh, capability to send more information uh, through a communication channel within a unit period of unit duration of time, within a single time. So the reason I'm bringing up this idea is that for most of these communication processes, we need to have some sort of amplification, and amplifiers are really important for our regular purposes. So in the first chapter of this booklet, we're going to talk about amplifiers. Before amplifiers, we have a little bit of background. So I'm starting from here. The first thing that we have is gathering and communication information. This first bullet tells us that what is the basic way that communication work usually happens. So we have a box diagram over here. It goes pretty simple that we have a sensing device, then we have a processing unit, then we have an output device. Think of a human being. Let's say someone calls up my name, uh, then I hear it through my ear sensor. It gets processed in my brain that someone is using something that belongs to you, but you don't use it often, but they use it more often, your name. So I sense that. Then I could give some sort of response. I could either respond to them, I could get away from them, I could get closer to them, I could hide in darkness, I could show up in light. So I'm going to do something based upon knowing that someone is looking for me. So that's my behavior. So any type of signal processing requires these three boxes to be fulfilled. You have to have a way to sense the signal. You have to have to process the signal in the way that you want the output to become, and then you have to have certain ways to output that signal to show some relatable outcome for that signal. So that's basically given over here. So you can read through it. If you have any question, you can ask me later on. I'm going to give this as a homework, for a reading homework after this class. A couple of electrical devices are there which can help us a lot for sensing a lot of different scenarios. Excellent. Amma mauna sehane. All right. So this is one of the devices that LDR, light dependent resistor. This is the device that is capable to sense variation of brightness of light intensity. So how does it behave? You already know that LDR has a high resistance in darkness. It has a low resistance in bright light. So these two behavior, resistance versus brightness or intensity of light, they are inversely related. I'm not going to say inversely proportional. Inversely proportional would mean that if a certain, it would mean that none of this curve of resistance versus temperature, resistance versus intensity of light should become asymptotic on both axes. So at a certain darkness value of light, you should have infinite resistance for the LDR, but that's not practical. So I'm not going to use the term inversely proportional. It's better to use the word they're inversely related, which is true, that one increases, the other one decreases, and vice versa. And then we have thermistor. This one detects can detect the variation of temperature. Similar stuff, high temperature, low resistance, low temperature, high resistance. There is a certain graph that is included over here, which gives us an example of how does the resistance of a thermistor varies with the increase of temperature. You can see over here that this was for a thermistor, for especially for one thermistor. Every thermistor is not going to have the same graph. You can change the shape, not shape, you can change the values of the different parts of the graph by controlling the constituent parts that make up the transistor. So it's not a constant how that that every transistor would look exactly like this. However, what I want you to look at is that when in this graph, when the temperature is 0 degrees Celsius, you have a measured value of resistance, which means this graph does have a y-axis intercept. As you're slowly increasing the temperature, the resistance is going down. You can see it's not becoming 0. Technically speaking, the resistance of a thermistor will never become 0. Having the resistance of a thermistor becoming 0 means it has become superconductor. Superconductivity is also a certain thing that is achievable by human beings. We human beings have found out how to make something superconducting. Superconducting means the idea of superconductivity is not included in the syllabus, but just a quick hint. The idea of superconductivity is that if you can design or maintain or operate a certain electricity conductor in a way that it does not have any resistance whatsoever, or in other words, that whenever the electrons are going to flow through that material, the electrons are not going to experience any hindrance whatsoever. That thing is called a superconductor, and the way it carries those electrons is called a superconductivity. It's not a part of the syllabus, so what I want you to understand that for your knowledge base, you have to take into effect that as temperature will increase, the resistance of the material is going to decrease. That's it, but not become 0. Then we have third device, which is called the Piezoelectric Transducer. Have a look at the read for the heading that says candidates should be able to show an understanding of the action of a piezoelectric transducer and its application in a simple microphone. So take a good look what this thing says. A transducer is any device that converts energy from one to another. Piezoelectric crystals such as quartz have a complex ionic structure. When the crystal is unstressed, the centers of charges of the positive and the negative ions bound in the lattice of piezoelectric crystal coincide. It means if you find out an average distribution of positive charges because of the nucleus, and you find out the average distribution of negative charges because of the electrons, those two variations would perfectly match. Which means, like they say, pretty much like the way we discuss this thing for the capacitor, that how at atomic level does a capacitor actually store energy. Whenever we don't apply any voltage, the center of the positive charge and center of the negative charge, they coincide, which means the atom is not deformed whatsoever. But whenever we apply a certain voltage across the dielectric medium, then positive charges shift slightly to the negative plate, and the negative charges shift slightly to the positive plate, which makes some atomic level deformation within the atom of the object, making it store energy. And that's how the capacitors always store energy. So this is a very interesting and important idea that we need to consider, that we are going to, that piezoelectric crystals also pretty much work the same way. They have a complex structure. We are using the word complex because we don't want to get into how this actually happens for the piezoelectric crystal. However, normally if it's unstressed, means if we haven't compressed it or if we haven't elongated it anyhow, if we have kept it in the same original shape that it has naturally, then those charges will coincide. However, it says further here, right over here, a voltage will be generated across the crystal. uh, আচ্ছা না এখান থেকে, if however pressure is applied to the crystal, the crystal will distort and the center of the charge of the positive and negative ions will no longer coincide. A voltage will be generated across the crystal. This effect is known as the piezoelectric effect. See also the section on 29H. So 29H is a part which is from the earlier part. Electrical connections can be made to a crystal if opposite sides of the crystal are coated with a metal. The magnitude of the voltage generated depends on the magnitude of the pressure applied to the crystal. The polarity of the voltage depends on whether the crystal is compressed or expanded, increases or decreases in the applied pressure. So I'm going to now discuss in detail how does the piezoelectric crystal work to the level of detail that your syllabus requires you to understand. So I'm going to jump to this heading and then I'm going to come back to this paragraph once again. So this is what the piezoelectric crystal thing is about. This is the thing. 29H. Can you should be able to explain the principles of generation of and detection of ultrasonic waves using piezoelectric transducers. Now, in this case, it is applicable, is they have used the word ultrasonic waves, but it is not exclusive for ultrasonic waves. Normal, regular sound waves also work with piezoelectric transducers. And you have to understand one thing, that whenever I'm talking to the sound, let's say I'm now making some voice with the vocal cords in my throat, and this is vibrating the air in front of me. The microphone is able to pick up that sound. What essentially is in the microphone that enables it to pick up that sound? Now, you might think that we can have that figure that we saw a little bit earlier, that there was a cone-shaped microphone. We're going to talk through it. It's going to move a certain solenoid coil within a fixed magnetic field, which is going to generate some voltage. This is actually a practical design for a microphone. It is a practical design. But the problem with this design is that there is a limit for how much frequency of sound this device can handle, because whenever I'm making the sound in the atmosphere, I'm making series of compressions and rarefactions, and my voice might have a certain frequency that I'm talking about, which I think I can find out my general frequency. I cannot use live input. I actually don't know what my frequency is. I could get my de Broglie wavelength for one thing if I do the calculation, but that is not essentially my voice pitch. Oh, no, 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 no. We don't need. Where do I press allow?
That was something I was trying to figure out.
Is this some sort of a joke?
স্যার জাস্ট ওই অ্যালোতে চাপ দিয়ে দেখেন তো।
I am. Nothing is happening. This is some sort of a joke, I believe. Acha, never mind. Apparently, I cannot find a way. But this is not supposed to happen. We have an online tuner. Ah, allow. Yes. Now let's say I'm gonna do a single frequency sound. You can see that how much varied my voice is whenever I'm talking to the microphone. It has a lot of quality and a lot of ups and downs. So if I just make a normal sound, let's say around 95, what I see over here, and then if I go that sounds 370, and then go I cannot really make a very bold sound like that's the most bold I can make. Sorry about that. So the reason I'm trying to show you this thing is to give you an understanding that whenever we make sound, we make a lot of different vibrations, and our vocal cords vibrate in that pattern because our vocals are designed to do that. Thank you very much. Our vocals are designed to do that, but the device which should pick up our voice in its original form should be also able to have the same amount of responsiveness for those devices. And this was only for a human device, and there can be other microphones can be also used for picking up acoustic sounds. For example, the music out of an acoustic guitar or a violin or a cello or a piano, acoustic piano, that is, not electric piano, not keyboards and other stuffs. So we need to have to have a receiving end which can have reaction time. I'm not reaction. I mean, I'm trying to use the word responsiveness that matches with the requirement of the output device. For the reason I'm telling you this is that if you think that if we want to use a solenoid-based microphone, then we have to make that vibrating part of the microphone extremely light so that it could vibrate at any of the frequencies that we shoot at it. That would require the microphone to be made very light and very, very subtly attached in the magnetic field. And designing a thing, physical object in that manner, which should also last long, is actually quite difficult. That's where the piezoelectric crystal slash the silicate crystal actually will come in. Sorry, quartz crystal actually comes in. So we're gonna have to see about the quartz crystallite over here, but I really find this sound amazing. Kids, just hold on a second. I'm gonna try something. For example, an LDR to be used within a fixed circuit. Yeah, an LDR to be used as a part of a circuit. So the variation of resistance can be read as a variation of voltage that happens across it. So it's an electrical information output. Similarly for thermistor, then here is the piezoelectric transducer, which is also giving out voltage. The reason we are so interested about the output side to be an electrical information, because we can process the information with electrical circuits. That's how our application capabilities for human beings or researchers have gone through. But if you come to think about it, it can be something else if we human beings develop in a different track of knowledge. For example, if we human beings were developing bionic or biological equipments earlier than the electrical development, if our knowledge actually approached that way in the path of the history, then we might as well want that every sensing device would be able to sense something, and then they would be able to give a biological output, some sort of like that. So maybe that would be also happening. But in this case, our aim is to make the output to be electrical. So that's the important fact that I would like you to understand. I'm just going to finish reading this paragraph so that we can move on from here. Have a look. So this central one is the silicon ion, and these circle ones are the negatively charged oxygen ions. So this is basically this is not actually hexagonal like this. This is actually called a tetrahedral structure. Yeah, tetrahedral circle. So quartz is a complex structure made up of large number of repeating tetrahedral silicate units, as illustrated in figure 2.1. The position of the oxygen links are not rigidly fixed in these units or lattices, and since the oxygen ions are negatively charged, movement can be encouraged by applying an electric field. When the crystal is unstressed, the center of the charge of the positive and negative ions bound in the lattice of the piezoelectric crystal coincide. So their effects are neutralized, as shown in figure 2.17a. If a constant voltage is then applied across the electrodes, example, the layers of the silver, the positive silicate ions are attracted towards the cathode and the negative ions toward the anode. This causes the distortion in the silicate unit. So what they're telling us over here is that if we apply a physical voltage, we can achieve this vibration. We can achieve this compression state. If we apply a reverse voltage, we can get this state as well. So which means we can make the silicate crystal vibrate in the way that we're going to apply the voltage as well. So what I was discussing for the earlier part is that if it is physically made to undergo compression or rarefaction, it will be giving us the voltage. Vice versa, if we physically apply the voltage, this crystal will react to that voltage and eventually become compressed or extended. So it says that if a constant voltage is then applied across the electrodes, that is across the layers of the silver, the positive silicon ions are attracted towards the cathode and the negative oxygen ions towards the anode. This causes distortion in the silicate units. Depending on the polarity of the applied voltage, the crystal becomes either thinner or thicker as a result of the altered charge distribution. These effects are illustrated in figure 2.17b and in figure 2.17c. An alternating voltage applied across the silver electrode will set up a mechanical vibration in the crystal. So in this case, they were talking about if we apply a fixed voltage. So for one type of voltage, you're going to get compression. For another type of voltage, fixed voltage, you're going to get expansion. But if we now start to apply alternating voltage, this crystal is going to start to vibrate. An alternating voltage applied across the silver electrodes will set up mechanical vibrations in the crystal. And if the frequency of the voltage, applied voltage, is the same as the natural frequency of vibration of the crystal, resonance occurs and the oscillations have maximum amplitude. The dimensions of the crystal can be such that the oscillations are in the ultrasonic range. So if we apply the voltage of this variation voltage by electrical AC electricity, which has a frequency higher than 20,000 hertz, that is the upper threshold for our audible range for us human beings, then that can be an ultrasound. The dimension of the crystals can be such that the oscillations are in the ultrasonic range, that is greater than 20 kilohertz, thus producing ultrasonic waves in the surrounding medium. Ultrasonic transducers can be also used as receivers. Here comes the part that I discussed. When an ultrasonic wave is incident on an unstressed piezoelectric crystal, the pressure variations of the alter the positions of the positive and negative ions within the crystal. This induces opposite charges on the silver electrodes and producing a potential difference between them. The volume potential difference can then be amplified and processed. So this is a very simple figure for this one. What you have to understand that here we have, this is the piezoelectric crystal. This is the piezoelectric crystal, the silicate crystal unit. We have a backing material over here. The reason we need a backing material so that the crystal does not physically get shifted because of the pressure variation. Rather, it is stacked against a solid surface, so that whenever the pressure variation comes out, it actually makes the vibration. We have a bit of a plastic cover over here, and we have two silver electrodes on these two sides, and a coaxial cable. Coaxial cables are actually type of cable which are very good for information carrying capability. Why it is good, we're gonna see it later, don't worry. So coaxial cable is used to feed this thing. This thing, this device is actually called, what is this thing? It is called, silicate crystal piezoelectric transducer. Yeah, this thing is actually called a transducer, or it can also work as a transceiver, which means if we send a high frequency alternative voltage for a short duration of time, for example, let's say we're going to send 25,000 hertz of AC voltage to this piezoelectric crystal for a duration of 0.1 second, or maybe 0.01 second. 0.01 second means you're going to have a lot of variation. You're not only sending one pulse, you're sending a lot of pulses, but that is very short lived in the ultrasound region. In that case, this is going to be affected by the voltage, produce the ultrasound, which can eventually flow forward. And eventually, if it is used as a medical probing device to detect stuffs within the body, these ultrasounds can go into the patient's body, get reflected from different sharpness of objects, and eventually it will be reflected back. Whenever these ultrasounds will be reflected from different layer of the inside the human body, the final layer happens to be the backbone. Then this piezoelectric transducer would now be affected by the reflected or reflection of the ultrasounds, which itself created. So it will produce sound, wait for the reflections. Then reflections from different locations inside the body is gonna reach to the same piezoelectric crystal after different time. Depending upon how much time has passed for receiving each of these reflections and how strong those reflections are, we can actually predict what are in front of this object. This is basically how a sonar works. Sonar means the sound used for navigation, and something, the mechanism for by which dolphins move around or submarines work. So this is basically a linear view for how the sonar works. We're going to send a sound, we're going to wait for the reflection is going to come by, then understanding with the reflection, we're going to understand what is in front of us. So this is not going to be keep on producing the ultrasound continuously. It's going to produce pulses of ultrasound, so because it will produce a large ultrasound pulse and wait for the entire reflection to be reached, and then it will produce another one to scan another line along the body. And if it will keep on doing this too many times over every second, and that accumulation of all of those data will give us a view for what is inside this patient's body. That's basically how an ultrasound scanning works. However, we're going to see about the ultrasound scanning part a bit later, but the behavior of the piezoelectric crystal, this is new for you, but does it make sense so far? No. I'm not muted, am I?
Yes, sir.
I'm muted.
না স্যার আপনি মিউটেড না, জাস্ট সবগুলো মাথা প্রসেস করতেছিলাম ওই।
Oh. Acha. You kids apparently are not asking questions, so I'll assume that you don't have questions. These are new stuffs. You have to remember them, learn them, be able to use them. So this is the
আচ্ছা
third.
স্যার,
Yes, follow.
স্যার ওই যে আল্ট্রাসাউন্ড ওয়েভগুলা কিভাবে প্রেসার ডিফারেন্স ক্রিয়েট করে?
কোনগুলা?
যে আল্ট্রাসনিক ওয়েভগুলা যখন রিসিভ হয় না, তখন বললো না যে রিসিভ হওয়ার পর এখানে প্রেসার ডিফারেন্সে পজিশনগুলো চেঞ্জ হয়, মানে নেগেটিভ আর পজিটিভ ট্রান্সফার। সো মানে এই প্রেসার ডিফারেন্সটা কোথা থেকে আসে? মানে আল্ট্রাসাউন্ডটা কেমন ভাবে মেক করে এইসব ডিফারেন্সটা প্রেসার?
Acha, this is very simple. Let's say, let me put it this way. Let's say whenever I am talking to atmosphere, the vibration of my vocal cords is going to set up a series of compressions and rarefactions in the atmosphere, which can reach up to the audience's ears. And their earlobe or eardrum is going to be vibrated based upon the compressions and rarefactions. So whenever the earlobe is affected by a compression, it is going to try to go inside the head, whenever it is affected by a rarefaction, it's going to try to come outside the head, because that's the whole idea of pressure variation. Physical objects are going to react to the pressure regions so that they can minimize that pressure variation. That's how everything works. So the piezoelectric transducer will also work in a way that is going to send a certain ultrasound pulse of high frequency. So there is a figure that I can show you. This is one of those figures that you have to understand as well, which I might as well told you later, but this is a very simple figure. Here they are trying to take an ultrasonic sound peak image inside a human skull. You might wonder, why inside a skull? I don't know why. They're just doing it. So we have a transmission pulse. This is the first pulse that we are sending, which is a very high amount of pulse. So this is the first pulse that we're sending. Then it's gonna enter through multiple layers of human skull, and the moment it's gonna change from one medium to another medium, a portion of it would be reflected. For example, the first we have the transmission from the piezoelectric transducer to the skin of the head. Then the skin will be perforated. It will hit the skull. Then the skull, which is the bone of the head, that will be perforated, and then it will enter into the first layer of brain. So we have 3 layers over here, hence 3 reflections, which is the skull echoes. Then it's going to travel through the basic material of the brain, which we are assuming to have no reflections in brain because it's the same medium. Every human brain, there is a median fissure, there's a crease at the center of the brain. From back to forth, the brain is not in 2 pieces, it is in 1 pieces, but there is a crease at the middle of the brain. So from that crease we can have another reflection, and it's gonna get other reflections from the other side of the brain as well, which is gonna be pretty much similar to this one. So it can essentially measure that how far these reflections are and what is the strength of these reflections are, and it can predict that whether the brain is healthy or not. For example, if there is a brain tumor inside the brain in a certain location, it might get some irregular from a healthy person reflection in some other place. For example, let's say if there is a brain tumor over here, it might have a significant reflection in this part, which is dissimilar from a healthy person's brain. That dissimilarity will tell us that there exists something additional in this person's brain that a regular person usually does not have. So that can be detected from that point onwards, and we can find out the exact location of that tumor and how big it is, depending upon what is the gap between the reflection of the 2 sides of the tumor. If the tumor is really large, then you're going to have 2 reflections and on 2 sides which are pretty wide. If it is small, then you're going to have pretty close reflections. So the piezoelectric transducer is capable to pick up all of this reflection information, reflection of the sound waves pretty strongly. But the question that you asked, that how does that happen? Whenever the compression if I just try to draw it for you, so let's say we are holding this piezoelectric crystal beside the head. Whenever compression comes and hit the piezoelectric crystal, for example, let's say, how am I going to draw compressions and rarefaction over here? Okay, let me just try. Let's say compressions, rarefactions. Okay, so let's say an ultrasound pulse is coming by. This is just one ultrasound pulse with 1 compression, 1 rarefaction. So whenever the compression is gonna reach up to this part, as long as the compression will pass through this part, through the piezoelectric crystal, this thing is gonna be compressed, because this means that the flesh medium, bone medium, they are in a compressed state because of the wave, which means they are naturally trying to expand outwards. Compression means what? The particles are squeezed in. So this will cause this crystal to become squashed, giving you 1 type of voltage. After this half cycle, whenever it starts to experience the rarefaction, then this piezoelectric crystal will try to expand outwards to accommodate the variation of pressure. So this is one thing. And another thing that I can show you, which I have saved to explain to O-level kids. I hope I can find this. I'd like to show you one more thing. And maybe I'm gonna get a copyright infringement for showing it on a recorded video, but I'm gonna show this to you anyway.
Hey guys, and welcome to my ride along Linux. Our change in pressure is, and below that we
Have a look.
have our pressure. Some things to point out and to show is that we can see in the representation of the sound wave right at the very top, we can see regions of denser particles and less dense particles as the wave oscillates. That corresponds to our compressions and rarefactions. Another two things to point out is that we have both
So this is just a visual representation for how the compressions and rarefactions actually affect the medium. Fine. Does that answer your question?
Yes, sir.
Okay. So that's that. So coming back to the part where I actually left off is that I talked about 3 sensing devices. First, it was LDR, then there was a thermistor. You have seen a graph of thermistor. Then the third one was a piezoelectric transducer. If you look at the spelling, spellings are important. The fourth one that we have, candidates should be able to describe the structure of a metal wire strain gauge. And F, candidates should be able to relate the extension of a strain gauge to change in resistance of a gauge. So this is a hypothetical view for a resistance wire strain gauge. So let me just explain what is happening over here. A resistance wire strain gauge is basically a piece of resistance wire which is coiled in this spiral shape. This is a spiral shape. It's not essentially a coil, it's a spiral coil or spiral shape, which is actually coiled in a spiral shape. Hold up, I have to sneeze. All right, I'm back. So the idea for this metal wire strain gauge is to able to detect even a very small amount of strain within a physical object. This was primarily developed for the aircraft industry to measure the strain that exists within the wings of the airplane. So let me just show you how this thing can work better. For example, I'd like to, let's say this is a device, and this rectangle that you can see over here, this is a fixed rectangle. It might as well be a plastic structure inside which the wire is perfectly arranged. So the wire cannot move away from this plastic structure. And if this plastic structure of the, or if this rectangular piece of object that undergoes some sort of lengthening or elongated length, the whole wire has to increase in length alongside. So one of the ways it works is like this. Let's say we have an aeroplane. So an aeroplane which is currently in ground. So whenever any aeroplane is in ground, it looks like this. Have you guys ever seen an airplane like this? Hold on, respond. Whenever airplane is in ground, it looks like this. This figure is not done to scale, so excuse the quality of the figure. What I'm trying to show you, if you look at the face view, front view of an airplane, on ground, the wings actually sag downwards. But whenever an airplane is in flight, this whole thing changes. Let's say now this is the wing of the airplane, face of the airplane. This is the black part of the nose, and there is the windshields. Whenever an airplane is in air, the wings actually become like this. They sag upwards. So there is a significant variation of compression and tensile stress and compressive stress on the top and the bottom side of the airplane. So to have a measure, we need to make sure that these airplane wings don't bend too much, because that might cause into structural failure, which means the wings might tear off in mid-air. So we don't want that to happen. So we want to travel at a safe speed, yet we don't want to be slow enough that it costs us too much fuel and too much time for the passengers. So we want to travel fast, yet not fast enough, too fast that is dangerous. So we can place some of the strain gauges over here. For example, if I now draw the top view of the aeroplane, let's say this is the top view of the aeroplane. So here's the aeroplane, and this is the tail of the aeroplane. This is the tail wings of the aeroplane, and let's say this is the large wings of the aeroplane. This is the top view. So what we're going to do, we're going to put these strain gauges lengthwise in this fashion, figure not drawn to scale, where these wires are going to be in parallel shape like that. So whenever on the ground, these things are going to be in a elongated state, then a flat wing, and the ones which are on the bottom they're placed in different places actually. They are going to be in some sort of a compressive state because the whole thing is curved downwards. Whenever the airplane is in air, these top parts will be in some sort of a compressive state because this is now curved inwards, and these bottom ones will become into some sort of an elongated state. So because of this, the length of the wires which is placed in this case so the length of the wires would actually change. So if the strain gauge undergoes extension, the whole strain gauge will extend, and you're going to have a lengthening of these wires. These vertical parts are not lengthening very much, but these long parts will lengthen or undergo a large amount of length increase. If you wonder, why do you need so many wires? Why not only one wire? The idea is the amount of increase for one wire length is actually very small. We're talking about bending of the wings. So, and these things are not like 1 foot, 2 feet long. These are pretty small devices. Might as well be 1 foot long, but they are significantly smaller than the length of the wing. So if we have a lot of wires undergoing the same amount of length increase, then measuring the variation of the length is easier. So let's say if one of these wire actually increases by, let's say, 0.1 millimeter, and if you have tens of these wires over here, in total if this 0.1 millimeter length increase gives you a certain rise of resistance, which we're going to measure from the applying some voltage across these 2 points. Measuring this resistance is somewhat difficult compared to if you have 10 of these wires parallel. For example, in this case, we don't have 10, we have 1, 2, 3, 4, 5, 6 of these wires. So if this whole structure extends by 0.1 millimeter because of the extension, then the total length increase for this set of wires would be 0.6 millimeter, right? And that was going to give us 6 times the resistance increase compared to what we would have got for only one wire. So measuring this thing more precisely is significantly easier compared to measuring this thing with a much higher amount of reliability, because this value is certainly bigger. That's why we need so many different wires. So that's the whole idea of this one. And then when this whole thing is going to undergo some sort of compression, then that's going to give us some other type of resistance decrease. Now, one thing you have to understand, the idea for resistance goes like this: resistance proportional to length, and resistance is also inversely proportional to cross-sectional area. Now, or we can write R equals to rho L by A. You know, the rho is the resistivity of the, which is a property of the material of that, which is the property of the material of the wire. Now, for the whenever the wire will undergo increasing length, try to understand. If you try to visualize this wire as a single piece of wire, which is a cylindrical shape, let's try to visualize that this is a wire which is in a cylindrical shape. If you start to extend it on both sides, it's going to increase in length. Wouldn't this essentially cause the wire to become thinner? Think about it. Bolaban, respond.
Yes, sir.
If we do the whole thing in the same temperature, the volume of the wire is not supposed to change. So if we lengthen it, that essentially tells us that we're going to have some change in its cross-sectional area. So here's the deal. Try to understand. If you look at this one, so whenever length is increasing, resistance will increase, and an increase in length will also cause a decrease of cross-sectional area. This will also result in an increase of resistance. So lengthening will essentially do resistance increase by both of these factors. This is the true mathematical scenario. And the reverse is also applicable. If it is compressed, the length becomes smaller, cross-sectional area becomes bigger. So both of these factors will reduce the resistance. For the sake of simplicity for your syllabus, what the say people have decided that we're going to consider the change of this cross-sectional area negligible. We are interested about the change of the length only. And we have used so many layers of wire because we are very much interested about the length and exclusively about the length. So they are not going to consider the this part of the equation, not this variable. The only thing that they're considering that R is proportional to L. So delta R will be proportional to delta L. So you have two proportionalities which should have the exact same proportionality constant. So if you divide one by another, let's say this is equation number 2, which is proportionality number 1, and if I divide 2 divided by 1, what I'm gonna get is delta R by R equals to delta L by L. Interesting enough, we can know the original resistance of the wire from some ground experiment. We can measure the delta R by measuring the voltage and the current that flows through this device. So this delta R has to be measured precisely. We know the actual length of this thing, which means the delta L can be known as well. Or even if we don't bother to know this thing, we can actually measure how much is the delta L by L ratio altogether. If we measure the delta R, we can very precisely measure the delta L by L, this whole ratio. And if you should remember from your elasticity chapter, this ratio is what we call strain. If you know the value of strain, and if you know the what is this thing called? Young's modulus, or of the whole wing material. Remember, using the formula Young's modulus is also stress over strain, you can calculate the stress of that part of the wing at that instant. So all of these things are fed into a simple algorithm, and eventually the pilots will see that how much stress is at certain location on the wings, or what is the maximum stress at any location of the string. So the computer of the aircraft will automatically detect all of these things, do all this calculation, and present to the pilots or the engineers the data that they are interested in. So this is how the whole thing works, and this is the key equation by which we might have to do some mathematical problem to handle. So this is our fourth detection device. This detection device can detect deformation, which is also giving us a electrical output because we want to use it as an input device. So in this case, the input is the physical deformation, compression or rarefaction in a larger scale on physical bodies, solid objects to be more precise. And we can detect that by applying this device, which is called a metal wire strain gauge. It's a mouthful, but that's just the name. So have a look. Metal wire strain gauge. This whole thing is the name of this thing. So yeah.
Sir, actual aircrafts এর মধ্যে how is this held in its place? মানে the wire and the plastic.
These things are braced or nuts and nut bolted on parts of the airplane wing. Braced means it is either glued, either with some metal glues or with some silicone glues perfectly with the surface of the metal, or this thing actually might be slightly longer than it I have drawn. For example, let's say if I paste it again. Oops. This is a very simplified view. You have to understand that it is possible that we can have a bit of extension like that, and we might as well have locations for nuts and bolts in these places, which are going to be attached to the airplane wing of that location. And the wires are going to come out, and that will be connected to some sort of circuitry which will be able to apply a fixed amount of voltage from the battery of the airplane wing and then work with that measurement. Or to be more precise, if this is an airplane wing, so let's say I'm going to apply nuts and bolts on the two sides of this whole thing in two specific places on the ground. So whenever it will go in the air, it will become either closer or become more longer depending on which side of the wing it is connected to. It is not easily visible from the outside because placing these blocks of materials outside the wing would give us aerodynamic disadvantage. So they are in most cases attached on the inside of the wing. That's why we don't see them. Bucho.
Yes, sir.
Okay. So then we have a very common figure. What do you call this thing? Anyone know this circuit? Or remember this equation? No one?
So potential divider.
It's a potential divider, exactly. It's a potential divider. So a very, very basic potential divider circuit. So we have a big supply E. We have two resistors. In this case, F is represented as a fixed resistor, which for our circuit is a fixed resistor, but in other cases it can be a variable resistor. Variable resistor means manually operated variable resistor. And in this case, we have the lower resistor is a thermistor, and we're taking the voltage output out of it. So this thermistor is a sensing device, which is going to give us different voltages at different temperatures because its resistance will change. And how much voltage should we get from this output side can be given by this fraction. And if we can measure this voltage properly, then we can actually have a measurement of the resistance. And if we can feed the resistance versus temperature data within the brain of that machine, we can also reciprocate any measurement of resistance into relevant resistance measurement of temperature as well. And the device might as well be work as a thermometer, precise thermometer, if you ask me. So that's one way to deal with it. So we're going to be seeing a lot of this potential divider circuit in a lot of the upcoming figures, in a lot of orientation as well. So orientation is going to be a challenging part for us to make sense of it. And then comes this thing, which is called the operation amplifier. Can you be able to recall the main properties of the ideal operation amplifier? Now, this is an interesting word. Have a look at this word. What does it mean? When you see this word in a physics topic, what does it mean?
It does not exist in the real life scenario.
Exactly. And that's one very unique thing that I would like to hear. And what is the other thing? Or is there anything else apart from that? It does not exist. True. So, and the other thing that I believe is applicable for the word ideal is that we're going to learn highly simplified information of a pretty complicated thing. So, like ideal gas, like simple pendulum, these things don't exist in real world. By definition, they don't exist in real world. Similarly, ideal op amp doesn't exist in real world. So we're gonna learn to work with a highly simplified version of the original device. Now, a couple of things to remember. This circuit view for the operation amplifier is confusing, slightly confusing, because of the way it is labeled. It comes with 5 ends, and inside there are a significant arrangement of transistors and stuffs. This is the circuit symbol. Given to the triangle, it has 2 input sides. One is called the inverting input, and the one is called the non-inverting input. And for reasons unknown, they are labeled with minus and plus. They could as well label this as I and N, inverting, non-inverting, but they didn't. Whoever made this circuit symbol decided that we're gonna give this a minus, we're gonna give this a plus. So the minus label input side is the inverting input, that's just the name. The plus side is the non-inverting input, that's just the name. These signs of minus and plus does not anyhow whatsoever imply that a positive voltage should be applied on the non-inverting and a negative voltage should be applied on the inverting. This does not ever mean that. We could apply any type of voltage, alternating voltage, constant DC voltage, ground, zero voltage at any of these inputs. We can do whatever we want, but they are labeled with minus and plus because whoever came up with the circuit symbol for this thing decided to label it with minus and plus. So this minus and plus doesn't have any physical significance or about which type of voltage are we going to apply here. We can apply any type of voltage. You just have to remember the minus labeled end is named the inverting input, which is important for us, and the plus labeled end is the non-inverting input. And then we have the whole thing. This is the these are the 2 input sides where we're going to send the input signal, or we're going to feed the device the weak signal. This device is going to take in that weak signal, and then it will amplify this output using the supplies. The supplies are there so that this can produce a high output. So what I'm trying to tell you is that if you give electromagnetic, if you give this, if you put a sinusoidal wave of, let's say, of amplitude of, let's say, 0.1 volt, and you want an output of, let's say, 2 volt, so you are increasing this signal by 20 times. So you are increasing joule per coulomb. So you're inputting 0.1 joule per coulomb, but you want an output of 2 joule per coulomb. So you have to increase the amount of energy by 20 times. But energy cannot be created or destroyed. It can be only transferred from one form to another, from one place to another place. Which means if this device have to work as an amplifier, if this device have to increase the voltage of an input signal, it has to feed some energy. That feeding of the energy is where the supplies come from. Typically, we have the positive supply connected on the top and the negative supply connected at the bottom, but there is no hard and fast rule for this. In certain figures, we can also have the negative supply on the top or the positive supply at the bottom. In some cases, the supply wire connections might not as well be shown. Assuming that they're connected to the supply somehow, we might as well only show these wires floating in air just to reduce the complexity of the circuit. In some figures, you'll see that op-amp is only drawn by the triangle and the 2 input wires and 1 output wires. The supplies are not at all shown. But that doesn't mean the supply is not there. An op-amp cannot function without a supply. Supplies, if not shown in the circuit diagram, means that they were omitted because we did not want to make the circuit more clumsy, more complicated than it already looks. To reduce the complication appearing in the circuit diagram, we decided not to show the supplies, but the physical supplies do exist and they have to feed with a certain amount of voltage, which will be provided by in the question. So whether the circuit shows or not, supplies will be there. Normally, positive supplies are on the top side, negative supply on the bottom side, but this is not, there is no hard and fast rule for that. These two sides can also vary. Although we're going to have 2 inputs, we're always going to have only 1 output. This is pretty interesting. Why do you need 2 input and why do we have only 1 output? The thing is, whenever we're going to give op-amp a signal to amplify, we have to tell the op-amp what is the base value compared to you should amplify that. The op-amp is going to amplify the difference of these 2 inputs and amplify that as the output. So what I'm trying to say is that if I tell you that in one of these input sides, let's say we are providing an input of, let's say, 0.1 volt, and we want an output of 2 volt. Now, if you want to make 0.1 into 2, you understand that we are making an increase of 20 times. But that 20 times increase is based upon which starting value of the voltage? That will be 0. I mean, from 0 to 0.1, you have 0.1 magnitude, and from 0 to 2, you have a magnitude of 2. So for the op-amp to work, one of the end has to be fed for it to give a sense of ground, that this is my lower limit. Whatever the other input is differing from that ground value or from one of these value, I will amplify that amount. If it is not making better sense, it might better sense a bit more if you have a look at this equation. Have a look. The output voltage of an op-amp is given by A naught. A naught is usually the default amplification multiplier, which is usually called the gain. This thing is called the gain or open loop gain. Gain means the multiplication factor, into V plus minus V minus. V plus minus V minus means the difference between the non-inverting and the inverting input, and it is always given like this. This V plus minus V minus is basically what is called the input voltage. So input voltage is the difference between the non-inverting input and the inverting input. It is not big minus small. Don't make a mistake. If this is 0 volt, this is negative voltage, you do 0 minus negative. If it is 0, if this is negative voltage, you do 0 minus negative minus 0. We are always going to get the input voltage by this expression, V plus minus V minus. So V out equals to A naught into V plus minus V minus, which means the output will always be multiplied. Output is the multiplication of the gain value of the op-amp, which is a certain number, that how much amplification can it do, multiplied by the difference of the 2 input sides. So we're going to do that and get this output over here. So then it says energy supply gain of the op-amp. The ideal operation amplifier has the following properties. The ideal operation amplifier has the following properties. So we have infinite input impedance, which means no current enters or leaves on either of the inputs. We have infinite open loop gain, zero output impedance, infinite bandwidth, infinite slew rate. These are the common 5 properties, and এই 5টা property থেকে আমাদের কোশ্চেন হয় এবং এগুলোর মিনিংও জিজ্ঞেস করে। Now let me explain part by part what does this mean. I'll draw some stuff. Actually, I can steal this figure. Why not? This is the symbol, circuit symbol for an ideal op amp. Now, what is it that I want you to understand? The first property was said to be zero input impedance. তাই না? Sorry, infinite input impedance, then infinite open loop gain, zero output impedance. I might as well copy it. দেখার থেকে কপি করা সহজ। Okay, let's keep it here and go bullet by bullet. Infinite input impedance. Okay, let me just tell you what is the idea for impedance is. The definition of impedance is not included in your syllabus, but in the properties of op amp, we have to use the term impedance because it is defined as impedance. Now, I'll tell you a little bit of discussion, give a little bit of discussion to explain what impedance is. Let me give you a very simple idea. Try to understand this part. If you have a solenoid coil, because of the wire of the solenoid coil, this will have some resistance, right? Think about it. It's a wire, you have some resistance. If you try to run an AC voltage, so I shouldn't have write A. If you want to flow an AC through this coil, the coil have some resistance, of course. So I did not draw an additional resistance. The coil will naturally become magnetized, demagnetized, oppositely magnetized, demagnetized, magnetized, and go under this circle. Becoming magnetized is not a natural state of this coil. By Lenz's law, the coil will try not that to allow, which means because this is a solenoid, not a single piece of wire. If it was a single piece of wire, then this would not be the case. Because it's a coil of wire, it's a solenoid. Along with the resistance, we're gonna also have some magnetic hindrance. We're gonna also have that. Physical resistance of the wire will oppose the current flow. The tendency for not being magnetized will also oppose the current flow by some amount. Together, these two things is what is called the impedance. এই আইডিয়াটা কি বোঝা যাচ্ছে? বুলামান?
Yes, sir.
স্যার এটা একটা স্ট্রেট ওয়্যারের জন্য কেন অ্যাপ্লিকেবল না?
Because whenever any wire, any straight wire is allowed to flow current, it produces a magnetic field which extends outwards and does not affect itself back. But in a coil, the magnetism of one coil affects other parts of the coil. They are stacked after each other. বুঝছো কি?
No, sir.
I mean, if you have a single piece of wire, you'll have concentric cylindrical shaped magnetic field lines, shell type of magnetic field orientations by right hand grip rule around it wire. These magnetic fields would be extending outwards from the wire to infinite directions, right? This field is not going to come back to this wire to affect its own property. Whereas for a solenoid coil, the magnetism of one coil affects the next one. This one affects both of them. This one affects all of them. So each coil affects all the other coils because they are aligned side by side. So it is an internally affecting structure where a single piece of wire is not. বুঝছো কি?
So this means the rejector turner যে magnetic field it cuts the adjacent coils. তার জন্য হচ্ছে
It affects all the other coils.
all the other coils. Yes, sir.
Just to make a bit more understanding about the impedance, which is not required, although I'm gonna give a small definition for you so that it can make a bit more sense to you. Have a look. Electrical impedance, measure of the total opposition that a current or a part of a circuit presents to electrical current. The total opposition. Impedance includes both resistance and reactance, which comes from here. We have impedance, which is coming from resistance. Inductive reactance, I talked about this part. I did not talk about the capacitive reactance because I'm not very comfortable with this thing, but apparently this is also included here as well. So I'm not very sure about that. I don't actually know how to calculate impedance. I just try to give you the idea for what impedance is. If you have a look over here, that's basically the definition. That's all I wanted to actually highlight. Electrical impedance is the measure of the opposition that a circuit presents to a current when a voltage is applied. So it's not only the electrical resistance, other type of hindrance, magnetic hindrance and capacitive hindrance, apparently together all of these stuffs make up the total hindrance for the flow of current, which is called the impedance. So because in the op-amp, in many / most cases, we deal with alternating inputs, so impedance is a pretty important factor not to be overlooked for the op-amps. So that's the idea. For your easier understanding, you can simply remember the idea of impedance as resistance, just to make better sense to you. But whenever you are writing in words, you have to use the term impedance for op-amp applications. The unit for impedance is also ohm. The unit for impedance is also ohm. It's measured in ohm, but it's just the combined effect. So that's what I want you to understand. So infinite input impedance means no current enters or leaves either of the inputs. This means that, let's say, to make the whole thing work, we're going to apply two slightly different voltage across this thing. Why slightly? Because the input signal is supposed to be weak. Let's say on this side, we're going to connect ground, which means this is 0 volt. On this side, we're going to connect minus 0.1 volt. So you do understand there is a bit of a voltage difference across these two parts. The infinite input impedance means no matter how much voltage do we have between these two ends, there will be no current flow from any of this terminal to the other through the op-amp device whatsoever. It means you can physically try to visualize there is infinite resistance between these two ends of the op-amp. No current flow can happen from any of the input to the other one. None whatsoever. This is the first property. Second property is that infinite open loop gain. Infinite open loop gain means what we found out in the equation, that the output of an op-amp, Joshim, is given by infinite open loop gain multiplied by this ratio, which is also can be written as V out equals to A naught into V in. To be honest, এখান থেকে আমরা A naught কে define করতে পারি. A naught is actually given by the output by input voltage. Anyway, just a minute, trust all the. On the boom. The amount of trust all. না লাগবে, আমি রাতে জাগবো। So this is the gain for the op-amp equation. So infinite open loop gain means for an ideal op-amp, this value is infinitely big. This value is infinitely big, which means even if we provide a very small voltage right over here, like too small, this output should also be infinitely big. But the question is, can the output voltage of a physical device, which is supplied by a limited measurable supply voltage, can become infinitely big? That answer is no. Because you cannot get infinite energy out of a measurable amount of provided energy. So this supply cannot give you infinite output. That's not going to happen. That's where the idea of saturation comes in. I'm going to tell you what the idea of saturation is right now, and might as well close our class at this point. I'm going to cover these 3 points in the next class, so we're quite about the time. So have a look at the idea for saturation. Let me explain this part. Let's say without considering any circuit, we have a situation like this. A typical regular real op-amp has an amplification factor of about 10 to the power 5. This is just an average value. It can be varied from op-amp to op-amp, but this is a typical value. If for a certain case, the positive supply line is plus volt and negative supply line is minus volt, which means we are supplying it a plus minus 9 volt supply, and the V plus is 1.4 volt and V minus is 1.3 volt, then how much should be our output be? Substituting these things in the equation, we get output should be 10 to the power 5, this is the value of the gain, into 1.4 minus 1.3, which gives you 10,000 volts. So math tells us that the value of this output is supposed to be 10,000 volts. But did we supply 10,000 volts to this op-amp? The supply voltage is only how much? Plus minus 9 volt. Which means even though the mathematical output gives us 10,000 volts, the op-amp cannot give us 10,000 volts. So what's going to happen? It's going to give us an output of plus 9.0 volt, because this calculation 1.4 minus 1.3 gives us plus output. So it's definitely going to give us plus 9 volt. So this is going to give us the limiting or the final value of the supply voltage. Whenever this happens, whenever any op-amp output becomes equal to the maximum value of the supply voltage, I'm using that a maximum to mean maximum plus or maximum minus. So either plus 9 or minus 9 for this example. Whenever the output of an op-amp reaches the maximum value of the supply, this is the state of the op-amp that we call to be saturated. This is something that we want to avoid for certain reasons, which I'm going to discuss next class. But this state that an output of an op-amp becoming equal to the terminal or highest value of the supply voltage, this scenario or this situation is called that the op-amp has become saturated. On the other hand, you can see over here that for a different example, if you have another setup, we have a supply line of plus minus 6 volt, but the V plus is 3.652 volt. You can see it's very small. You can see it's very precise up to third decimal place, and V minus is 3.654 volts. So there is a difference of only 0.002 volts. Even in this case, because the gain value is too large, 10 to the power 5, the output is becoming minus 200 volt, which means in this case also, this op amp is going to become saturated because it's going to give us an output of minus 6 volt. This means that this is the idea of saturation, that the output voltage of the op amp device becoming equal to any of the maximum values of the supply voltage. This is what we mean by becoming saturated. Now, this property says that infinite open loop gain, if there is only a very slight difference, very and slight, if there is only a very slight difference between the input voltages, it means if the V plus and V minus are even slightly different from each other, the output will be saturated, because technically speaking, this thing is proposing that the gain value is infinite. So if the gain value is supposed to be infinite, even if this number is extremely small, the product will give us an infinite value, which means the output will take one of the terminal values of the supply, depending upon what this subtraction gives. If this subtraction gives us plus value, this will be maximum positive supply output. If this subtraction value is negative, then it will give us the negative supply value, because it cannot simply produce voltage out of thin air. So maximum output can be only limited by the supply values. So that's the meaning of this second point. Have a look once again. If there is only a very slight difference between the input voltages, output will be saturated. Dash, the output will have the same value as the supply voltage. This is the meaning of the second bullet. এই বন্ধু বুঝা গেছে কিনা?
Sorry, যেটা হচ্ছে input, that's the inverting input, the one we are giving as the input.
Both of them are called inputs.
Sorry, দুইটা difference-টা আমি ঠিক confused হয়ে গেলাম যে non-inverting or inverting. Like, is non-inverting like acting as a ground যেটা দিয়ে মানে?
This is just for an example that I connected a ground over here. So for this case, my input voltage Vin would be 0 minus 0.1, so that would be plus 0.1 volt. That's my input voltage for this circuit. It could be other way around. I could have connected a 0 volt over here and connected other stuffs over here as well. Achha. I could have connected it other way around. The idea for inverting and non-inverting input is that we're going to have to connect two different things in these two sides, and the difference of those two ends is going to be amplified to the purpose of the mechanism inside the op amp. It's not defined which one should have ground or which one should have something else. You can provide anything in these two places, but whatever the difference between these two things, delta, let's say, that would be amplified on the output side. Did I answer your question anyhow?
Yes or no, sir. আমি যেটা বলছিলাম যে if we have a source which gives us a variable output signal, তো সেক্ষেত্রে তো আমরা একটা টার্মিনালকে এখানে কনস্ট্যান্ট রেখে তারপর হচ্ছে বাকি সিগন্যালগুলোকে অ্যাম্পলিফাই করার জন্য we can use either one of these terminals, right?
Precisely. So if you want to, let's say if I connect the non-inverting input over here, and let's say if we for this inverting input, other than connecting a fixed voltage, if you provide an AC supply of, let's say, 0.1 volt with 50 hertz of AC supply, let's say we're going to connect that one to here. In that case, the output is going to give us the saturated voltage value with a 50 hertz output. So you're going to have a small input voltage. Math tells us that for an ideal op amp, because the gain is infinite, that even when this value is something other than 0, the output has become infinitely big, and then when it becomes 0, it should be once again 0, and so on and so forth. But for practical purposes, there is a certain value. For example, let's say in this case, if the supply is plus 9 volt and minus 9 volt, so if this is the plus 9 volt value and this is the minus 9 volt value, we're gonna get flat curves like this. So whenever the input is negative, you're gonna get -9. Whenever the input is positive, you're gonna get +9. That's the type of output you're gonna get. Having the same frequency, but output is always saturated, but flipping from plus and -9 volt continuously depending upon the frequency of the input. Does that answer your question?
Yes, sir. বুঝছি।
Okay. Kids, thank you very much for the additional time of presence. All of you didn't leave the class. I really appreciate that. Some of you did, which is not a big deal. You can look it up later from the video lectures. I'll be uploading the photons and photography worksheet in 5 minutes. And yeah, let's try working on that out. Thank you very much. Good night.